Hi guys, so today we're going to be talking about waves. Just as a warning, this video will not touch upon light waves. I'm going to save that for another video, but let's get started. So what is a wave? A wave is a disturbance that transfers energy from one place to another. Waves do not transfer matter, only energy. For Regents physics, there are mainly two types of waves, electromagnetic and mechanical, but I'm only really going to talk about mechanical waves in this video. But that being said, let's quickly talk about electromagnetic waves. So these are waves in the form of radiation that travels through space. So what's special about electromagnetic waves is that they can travel through a vacuum. A vacuum is a space without matter or air, and all these different types of waves are on your reference table. On the other hand, mechanical waves travel through a medium. A medium is a substance like air or water that the wave needs to move through. These waves cannot travel through a vacuum, they need a medium. There are two main types of mechanical waves which we're going to talk about. So transverse waves have particles that move perpendicular to wave direction, so they move up and down. Longitudinal waves move parallel, so they move left to right. A key concept you need to remember is that sound waves are longitudinal. Now let's get into the different parts of a wave. So first up is wavelength. Wavelength is just the length of one wave, and we use meters to measure this. The symbol for wavelength is the Greek letter lambda. Now you're going to need to know how to count out one wavelength, and there's a few ways to do this. Basically, in a wave, you're going to have high points and low points. There's a middle ground called the principal axis where there are equilibrium points. The high waves are called crests, and the low points are called troughs. So crest to crest is one wave, trough to trough is one wave, but my personal favorite way to count out one wave is by labeling the points as A through E, and one wave is A to E. Now, moving on to amplitude. Amplitude is the maximum displacement of the wave. So from the principal axis, how high or how low does it go? Amplitude determines the energy of a wave. If there is an increase in amplitude, there is an increase in energy. Now, amplitude is also measured in meters. Now, frequency is the number of wavelengths that pass per unit of time. So, like how many wavelengths pass in 1 second. This is measured in hertz, and the formula is frequency equals 1 over period. By the way, I'm going to talk about period in the next slide. But for example, if 10 wavelengths pass in 2 seconds, that means there is a frequency of 5 hertz because 5 wavelengths pass in 1 second. Now, period is the amount of time it takes for one wavelength to pass. I used to get period and frequency mixed up like so much, so please memorize this. Frequency is the amount of waves that pass in 1 second, and period is the amount of seconds it takes for one wave to pass. Now, period is measured in seconds, and the formula is period equals 1 over frequency. As an example, if 10 wavelengths pass in 2 seconds, the period is 0.2 seconds because it took 0.2 seconds for one wave to pass. Now, this unit is super concept heavy, so there's not really any formulas. The biggest one you need to know is velocity equals frequency times wavelength, and another form of this is velocity equals wavelength over period. Now, there's a concept for the V equals F lambda formula. So basically, velocity of a wave stays constant. So the frequency and wavelength have to compensate. So if wavelength decreases, then frequency increases. And if wavelength increases, then frequency decreases. Now, moving on to interference. This is basically when two waves meet while traveling along the same medium. Constructive interference is when the waves are moving in the same direction, so they add up and get bigger. Maximum constructive interference is when the crests and troughs line up perfectly and there is a 0-degree difference between both waves, so the waves basically add up and it looks like it doubles in size. On the opposite end, destructive interference is when two waves interfere while moving in opposite directions, so the waves subtract from each other and look smaller. Maximum destructive interference is when the crest meets trough and there is a 180-degree difference between the waves. This makes the waves completely cancel each other out. Now, in and out phase waves have the same gist. So basically, waves are in phase when their points line up perfectly. So they can either have a 0 or 360-degree phase difference. Waves are out of phase when their points are misaligned. So if there's a phase difference of anything but 0 or 360 degrees, it's out of phase. When there is a 180-degree difference, it is completely out of phase. Now, standing waves occur when two identical waves move in opposite directions and interfere with each other. It almost looks like the wave is stationary when this happens. Now, you're going to need to know how to count out nodes and antinodes. This is pretty easy, so nodes are points at zero displacement and antinodes are points at maximum displacement. Finally, here are some key concepts, even though the entire unit is just concepts. So basically, the Doppler effect is when a point source of a wave is moving and to a stationary observer, it seems like frequency changes. So imagine a train is passing you, and as it gets closer to you, it's going to sound louder, but as it moves away from you, it's going to sound quieter. The actual frequency of the sound coming from the train is not changing, but to you, it seemed like it does. This is because of the Doppler effect. Now you're going to need to know what blue and redshift are. So redshift is when something moves away from you. If it mentions light, then the light will look red and the sound will be lower pitch. Blue shift is when something moves closer to you, so it will look blue and have a higher pitch. Now, resonance is when a vibrating object causes another object to vibrate at higher amplitude, and this occurs when the frequency of the first object matches the natural frequency of the second object. A big concept for this is going to be like an opera singer breaking glass. You see anything about resonance, immediately think opera singer. Finally, I cannot stress this enough, sound waves are longitudinal. Remember that sound waves are longitudinal waves because for some reason the Regents loves to ask about this. Now, I'm finally done explaining everything, so let's move on to some multiple choice practice. Number 1. Sound waves are produced by the horn of a truck that is approaching a stationary observer. Compared to the sound waves detected by the driver of the truck, the sound waves detected by the observer have a greater what? So this question is a concept question about the Doppler effect. So remember that Doppler effect is how frequency seems to change as the point source is moving. So in this situation, the truck is the point source, and in the perspective of the observer, the sound waves have a greater frequency because the horn of the truck seems to get louder as the truck approaches. So our answer is going to be D. Number 2. A tuning fork vibrates at a frequency of 512 Hz when struck with a rubber hammer. The sound produced by the tuning fork will travel through the air as a what? So this is a concept about sound waves. So immediately when we see sound waves, we should think longitudinal waves because we should remember that sound waves are longitudinal waves. So immediately we know that choices A and D are out because it says that the sound wave is transverse, which is wrong. Now, remember that longitudinal waves are parallel, so that means answer choice C is correct. Longitudinal wave with air molecules vibrating parallel to the direction of travel. Longitudinal is parallel and transverse is perpendicular. Number 3. The diagram below represents the wave pattern produced by two sources located at points A and B. Which phenomenon occurs at the intersections of the circular wave fronts? So they're talking about this area. So basically this is going to be interference because we can see here that two waves are interfering with each other. Number 4. The diagram below shows a transverse wave moving toward the left along a rope. At the instant shown, point P on the rope is moving towards the what? So this question is pretty confusing, but don't think about it too much. The wave is transverse, so its particles move perpendicular. So that means it's either going to be up and down. It can't be left or right, so C and D are out. Now the choices are between A and B. So if you imagine the wave is moving left, then point P will end up moving to the bottom down here. So our answer is going to be A. Number 5. The diagram below represents a wave traveling in a uniform medium. Which 2 points of the wave are in phase? So remember that in phase means that the waves are perfectly aligned with each other. So in phase points would be at the same position. So if we look at all the answer choices, A and E are the only points which actually align with each other as they are both troughs. So choice B is correct. Question 6. The diagram below shows a standing wave in a string clamped at each end. What is the total number of nodes and antinodes in the standing wave? So let's count out nodes and antinodes. Remember that nodes are zero displacement and antinodes are max displacement. So node, 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 antinode, 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 antinode. So there are going to be 4 antinodes and 5 nodes. 5 nodes. So that is going to be answer choice B. And remember, there's always going to be one more node than there is antinodes. Number 7, an astronomical body emitting high-intensity pulses of green light is moving towards Earth at high velocity. To an observer on Earth, this light may appear what? So it's saying that it's going to move towards Earth. So remember, since something is moving towards Earth, this will be blue shift. So this will appear as blue light. Number 8, two waves traveling in the same medium interference to produce a standing wave. What is the phase difference between the two waves at a node? So remember that standing wave is produced when two waves have the same amplitude and frequency but are moving in opposite directions. And opposite direction equals 180-degree difference. So this is going to be choice A. Number 9. The diagram below represents two pulses approaching each other. Which diagram best represents the resultant pulse at the instant the pulses are passing through each other? So we just add the pulses together, and since they're moving in opposite directions, the resultant pulse will look smaller and be in the direction of the larger initial pulse. So the answer is going to be C. This one's kind of just like common sense. Number 10. The diagram below shows a periodic wave. Which 2 points on the wave are 180 degrees out of phase? So my personal trick for this is to look at the degrees for each point. So remember that one full wave is equal to 360 degrees. So if we split the wave into parts, each point is 90 degrees from each other. So this would be 0 degrees. This would be 90 degrees. This is 180. This is 270. And this is 360. So 100 degrees, 180 degrees out of phase would be A to C. So that is going to be choice A. Number 11. The diagram represents two sound waves that are produced in air by two tuning forks. The frequency of wave A is 400 cycles per second. The frequency of wave B is what? So let's compare wave A and wave B. I'm going to use blue to show you guys wave A. So this is one wavelength for wave A, and I know this because I just look at the points. So A, B, C, D, E, that's one wavelength. A, B, C, D, E, that's another wavelength. So that's two wavelengths for wave A. Now wave B is A, B, C, D, E. This is one wavelength for wave B. So as you can see, if we do a ratio here, wave A is 2, while wave B is only 1. And this is because wave A produces two wavelengths in the same amount of time that it takes wave B to produce just one wavelength. So wave B has half the frequency of wave A. So the frequency of wave B is just half of 400. So that is going to be 200. So our answer is going to be B. Number 12. Transverse waves are to radio waves as longitudinal waves are to sound waves. So once again, this is just a big concept that you need to know. Sound waves are longitudinal. They're going to ask this a lot. Now, 13. What is the velocity of a water wave that it travels a distance of 10 meters in 5 seconds? This is really easy. We're just bringing back velocity equals distance over time, or technically like wavelength over time, but that's just 10 over 5. So our answer is going to be B, 2 meters per second. 14. Which graph best represents the relationship between the frequency and period of a wave? Remember that frequency equals 1 over period, and on these graphs, period is increasing. Now, if we look at this formula, frequency and period have an inverse relationship. So if period increases, that means frequency has to decrease. So our graph would be decreasing. The only decreasing graph here is D. So our answer is going to be D. 15. The graph below represents the displacement of a particle in a medium over a period of time. The amplitude of the wave is what? So remember that amplitude is displacement from the equilibrium position of the wave. So this would be 4 meters. So our answer is going to be D. 16. The diagram below represents a wave traveling in a uniform medium. Which characteristic of the wave is constant? So the answer to this question would be amplitude again, because the wavelengths are getting smaller, so wavelength, frequency, and period all change. But as you can see, amplitude stays the same because throughout the entire change, it's still at this height. 17. Base your answer to the following question on the graph below, which shows the variations in the speed of sound in air at different temperatures. When the temperature of the air increases from 20 degrees Celsius to 30 degrees Celsius, the increase in the speed of sound is what? So at 20 degrees, the speed is 344 meters per second, and at 30 degrees, the speed is 350 meters per second. So there's an increase of 6 meters per second. 18. Playing a certain musical note on a trumpet causes the spring on the bottom of a nearby snare drum to vibrate. This phenomenon is an example of resonance. So resonance is when one object's vibrations causes another object to vibrate as well. 19. The diagram below shows two pulses approaching each other in a uniform medium. Which diagram represents the superposition of the two pulses? This is super easy. The pulses are in the same direction, so they'll just add together. So 5 plus 10 equals 15, which is going to be choice A. Also, superposition is kind of just the same as like the interference adding thing. 20. A transverse wave is moving towards the right in a uniform medium. Point X represents a particle of the uniform medium. Which diagram represents the direction of the motion of particle X at the instance shown? So this is similar to question 4. It's a transverse wave. So the particles will be moving perpendicular or up and down. So we know that choices A and B are wrong because this is saying like left or right. Now, if you imagine the wave moving right, then point X would move up. So that's how we know that our answer is going to be D. 21. What is characteristic of both sound waves and electromagnetic waves? The answer choice is going to be A. They transfer energy, because remember that all waves transfer energy, not matter. 22. The diagram below shows a person shaking the ends of a rope up and down, producing a disturbance that moves along the length of the rope. Which type of wave is traveling in the rope? So it says that the person is shaking the rope up and down. That's our key word. So up and down means perpendicular, so this is going to be a transverse wave. 23. A wave completes one vibration as it moves a distance of 2 meters at a speed of 20 meters per second. What is the frequency of the wave? So we can use the formula velocity equals frequency times wavelength for this, and we just plug in. So 20 meters per second equals frequency, we're trying to find that, times 2 meters. So frequency is going to be equal to 10 hertz. 24. While sitting in a boat, a fisherman observes that 2 complete waves pass by his position every 4 seconds. What is the period of these waves? So remember that period is the amount of time that it takes for one wave to pass. So if 2 waves pass in 4 seconds, that means 1 wave passes in 2 seconds. So our answer is going to be 2 seconds. 25. An opera singer's voice is able to break a thin crystal glass when the singer's voice and the vibrating glass have the same what? So this is basically resonance. So the frequency of the singer's voice matches the frequency of the glass. So the glass starts vibrating and it breaks. So our answer is A. 26. Which is an example of a longitudinal wave? Every time you hear longitudinal, immediately think sound wave, because there are so many questions that talk about this. So the answer is D. Okay, so now we're going to move on to some short answer practice. So number 1, the speed of sound in a liquid is 1,498 meters per second. A sonar signal is sent straight down from a ship at a point just below the water surface, and 3.6 seconds later, the reflected signal is detected. How deep is the ocean beneath the ship? So we're trying to find the length between the ship and the ocean floor. It tells us that the sonar signal is sent from a ship, and this sonar signal is just the wave. And the reflected signal is detected 3.6 seconds later. This means that the signal went from the ship to the ocean floor, and then from the ocean floor right back to the ship. That was 3.6 seconds. That means it would have taken half that time for the signal to have just reached the ocean floor. So 3.6 divided by 2 is 1.8 seconds. So from the ship down to the ocean floor is 1.8 seconds, and the entire thing from the ship, ocean floor, back to the ship is 3.6 seconds. But we don't care about that. So it took 1.8 seconds for one wavelength to pass. So that means that the period is 1.8 seconds. So t equals 1.8 seconds. Now we need to solve for the actual wavelength, so we need frequency so that we can put frequency and velocity, which we already know, into the formula v equals f lambda. So frequency equals 1 over period, so 1 over 1.8 seconds is equal to 0.55 hertz. Now we can put this all into this formula. So 1,498 meters per second equals 0.55 hertz times lambda. So lambda, or wavelength, is going to equal 2,700 meters. And that's our final answer. Number 2. Water waves in a shallow dish are 6 centimeters long. At one point, the water oscillates up and down at a rate of 4.8 oscillations per second. What is the speed of the water waves? So don't let the word oscillations mess you up. This just means that 4.8 waves pass per second. So for letter A, it's basically saying that the frequency is 4.8 hertz because 4.8 waves pass within a second. Also, it tells us that the waves are 6 centimeters long, so 6 centimeters is equal to 0.06 meters. So now, in order to solve for speed, we can just put what we know into the formula v equals f lambda. So v equals 4.8 hertz times 0.06 meters. So velocity equals 0.29 meters per second. Now for 2b, it's asking us, what is the period of the water waves? So we already know frequency. We solved for it up here. And frequency is just, so period is just 1 over frequency. So 1 over 4.8 hertz equals 0.21 seconds. So our period is 0.21. Number 3, the diagram below represents two pulses traveling toward each other in a uniform medium. Draw the resultant displacement of the medium when both pulses are located between points A and B. So this question is asking us to draw the resultant, which is pretty easy. The pulse on the left has a displacement of 1 meter right here, and the pulse on the right has a displacement of negative 0.4 meter. Since these pulses are in opposite directions, they will cancel from each other and the resultant will look smaller. So basically just 1 plus negative 0.4 equals 0.6. So the resultant will have a displacement of 0.6 and it's going to be positive. So it's going to look something like this. Number 4. A musician plucks a 0.62 meter long string on an acoustic guitar as represented in the diagram below. The plucked string vibrates, producing a musical note called G. The waves traveling along the vibrating string produce a standing wave with a frequency of 196 hertz. On the diagram of the standing wave in your answer booklet, label one node with the letter N and one antinode with the letter A. So remember that a node is a point of zero displacement and an antinode is a point of maximum displacement. So a node would either be here or here, and an antinode would be here or here. Well, just here. But I labeled all of it, but just remember that for the actual question, you're only supposed to label one of each. Next one. Determine the wavelength of the standing wave on the 0.62 meter long vibrating string. So in the diagram, it shows us that the full standing wave is equal to 0.62 meters. But that is not a full wave, it's just half. Something like this would be a full wave. So this would also be equal to 0.62 meter. So in order to get the length of the full standing wave, it would be 0.62 meters times 2, which is equal to 1.24 meters. And that's our answer. Okay, next part. So calculate the speed of the wave traveling on the vibrating string. So it's asking for speed, so we just have to use the formula velocity equals frequency times lambda, because it tells us frequency right here, 196 hertz, and we just solved for lambda, which is wavelength. So velocity equals 96 hertz times 1.24 meters. and that equals 243.04 meters per second. Describe what happens to the frequency when the musician shortens the vibrating portion of the string by pinching the string against the fingerboard while the string continues to vibrate. Okay, so this is kind of like a concept. So if you visualize the string of a guitar vibrating and then you pinch part of the string, that section that you just pinched will stop vibrating. So if it stops vibrating, that means it's no longer like part of the wave. That means the wavelength will decrease. So let's write out this formula again. So velocity equals frequency times wavelength. So if the wavelength is decreasing, that means that frequency has to increase. So that means that frequency will increase. And once again, frequency will increase because wavelength decreases when he pinches the string since a portion of the string is no longer vibrating.